All right, so we're in the second part of 15.2. And we're going to talk about line integrals again on vector fields. So yesterday we talked about line integrals on scalar fields. Now, a couple of your homework problems today that come up, and I mentioned this a little bit yesterday. Several of your homework problems have to do with finding the mass of a wire, and that's a line integral problem, like I mentioned yesterday. But just as a reminder, the mass, if you have the mass of a wire is just going to be the integral over the curve of the density times the arc length. So your density function is going to be the function that you're integrating, and you're doing the line integral over whatever the path is, the shape of the wire. So there's several problems in tonight's homework that have to do with finding the mass of some kind of thing.
Wait, the ds is just the arc length from yesterday?
This is exactly the integrals that we worked on yesterday, where rho is your density. Rho would be your function. Rho would be f of x, y. So there'll be some density function that varies with x and y. And they'll ask you to find the mass of a wire in this shape with this density function. And this is all we're doing for that. All right, so today we're interested in finding the line integral over a vector field. Yesterday we wanted to integrate some function, some scalar function over a specific path. Today we're interested in integrating the component of a vector in the direction of our path over the path. So rather than the scalar function, we want to integrate the component of a vector in the direction of our path. So as a starting point, we're going to remember what we talked about with work last semester. And we said that work was our vector work, or work wasn't a vector, our scalar work is the force dot d, where the F was our force and d was our displacement vector. This gave us the component, the dot product gives us the component of the force in the direction of motion. So work was F dot d. So we're thinking finding the component of a vector in the direction of our path is similar to calculating work. So we're going to look at this in terms of finding work done by a force moving a particle along some path. So we have a force that varies with x, y, and z, and we are moving a particle along a path C. And C is a smooth curve. Just like we talked about yesterday. So this is how we're going to analyze this idea of finding the line integral of a vector field. So let's draw a picture of what we're talking about. Here are our axes. We have our three-dimensional coordinate system. Whoops. And we have our curve here in space, some arbitrary curve, and this is C. And we're going to use our argument that should be familiar by now. We're going to start here at P0, and we're going to go to P sub n This is the path that we're interested in. And we're going to divide this into little intervals. And we're going to look at this ith subinterval here. This is our delta S sub I. And our force here on the ith subinterval, I'm going to draw my force vector. That's the force at that subinterval. So that's the force at x sub I, y sub I, and z sub I. I'm going to move this. So that's our force in our ith subinterval. And I'm going to look, we want to find the work done by this force moving the particle through this ith subinterval. So let me draw a magnified picture of the ith subinterval. So here's my magnified picture. Here's delta S sub I. And here's our force vector. And that's at our position x sub I, y sub I, z sub I. And here is our tangent vector at the ith subinterval. And I'm just going to call this t sub I. So t is a tangent vector at the ith subinterval. So only the force acting in the direction of the tangent vector does work. So the work at the ith subinterval, so that any component that's normal to the tangent vector doesn't do any work on the particle at that instant. So the small increment of work on the ith subinterval, we're going to call that delta W sub I, is the force at our position and we take the dot product of the tangent vector. That gives us the component in the direction of motion, and it moves it through a distance of ds. And I don't want to use ds there. I'm going to use delta S sub I. So it moves it through a distance of delta S sub I. So the force, the dot product of the force with the tangent vector gives us our force in the direction of motion, and delta S sub I is how far we've moved it. And what we're going to do is sum this quantity over our interval and take the limit as delta S sub I approaches 0. So just like we've done before with so many other things. And we come up with our expression for the work. I'm going to go to the next page for that. So our work, if we sum over the entire interval and take the limit as delta S sub I goes to 0, our work is going to be the integral over the curve of f dot t ds. And just like we talked about before, we want some way to evaluate this. Now, we can calculate the tangent vector, and we could take the dot product with the force. And if you remember that our tangent vector, that t equals our unit tangent vector is r prime over the length of r prime. And sometimes calculating t was not often difficult, but sometimes it can be difficult. And then you'd have to take the dot product of this with the force. We want a little easier way to we want a little easier way to calculate this. And also remember that ds, for our parameterized curve, we parameterize our curve in terms of the position vector. So ds is the length of r prime times dt. And we've parameterized the curve by r of t. So r is our parameterization of our curve. So ds is r prime dt. So we can say that our work is the integral over our path of f dot r prime dt, and we also write that as the integral over our curve of f dot dr. So this gives us a nice way to calculate this line integral of this vector over the curve. So we're going to use this argument to define our line integral of a vector field. So we've gone through our argument, figured out what our sum is and how we can express a sum for this work, and we're going to use this analysis to make our definition. So we're going to define our line integral and our definition is that the integral over our curve of f dot dr is the integral over our curve of f dot r prime dt. And what we're doing here, just to make it more explicit, is we're integrating from a to b, and we're expressing our vector function, our vector field, as in terms of our parameterized curve. And this is where C is given by r of t, our parameterized curve, on the interval a to b. So very similar to what we did yesterday, we parameterize our curve. We express our vector function now in terms of the parameterized curve, and we take the dot product of that with r prime dt over our interval. Questions? All right, so let's look at a couple of examples of evaluating these. We want to evaluate the integral on our curve of f dot dr, where f is our vector field, is xyi plus yj, and our curve is given by our parameterized, our parametric functions, r of t equals 4 cosine ti plus 4 sine t j. From 0 less than or equal to t less than or equal to pi over 2. So this is our force. We could interpret this as this being our force, and we're moving a particle along this path from 0 to pi over 2. So first off, 4 cosine ti plus 4 sine tj, what is that path? Circle, and 0 to pi over 2 takes us first quadrant, so it takes us a quarter of the way around. So we're going a quarter of the way around this circle. So first, we need to express our force in terms of our parameters. So F, our vector field, is 4 cosine t times 4 sine t I plus 4 sine t j. So I've just written the field, the vector field, in terms of our parameters. R prime, I'm going to take the derivative of the parametric equations of our curve. So R prime is minus 4 sine t I plus 4 cosine tj. And F dot R prime, that's what my integrand is going to be. F dot R prime is minus 64 cosine t sine squared t plus 16 sine t cosine t. And we're going to integrate F dot R prime dt from 0 to pi over 2. So our integral over our curve of F dot R prime, or F dot dr, is the integral from 0 to pi over 2 of minus 64 sine squared t cosine t plus 16 sine t cosine t dt. That kid. I took that away from him in class yesterday.
Down the road.
Yeah.
It's one of those like plastic.
The the thing they had at the World Cup, and
Those things are so annoying.
Like I was riding down the road and he's just like out the window and I was like, what are you doing?
and this integral to evaluate, easy peasy, very straightforward, right? And we get minus 40/3. And now when we're integrating, when we're evaluating a line integral on a vector field, our result is a scalar. So we're not adding up vectors, we're integrating the dot product, so we end up with a scalar. So if you end up with a vector at the end, you've done something wrong. So the dot product always gives us a scalar. So we're adding up the components of the force in the direction of our path, along the path. Let's see, let me pick one other example to do and then we'll stop. We'll just do one more. What's that?
Better fit in 4 lines.
In 4 lines? I don't think it'll fit in 4 lines. Let's
Yeah.
let's do, we want to find the work. The work done by our force is given by yz I plus xz j plus xyk. moving a particle from the origin to the point 532. So here's our force, here's our path. Now, in order to evaluate our integral, our work is going to be the integral along our curve of f dot dr. In order to evaluate this, I need to parameterize my path. So we need to write the parametric equations of this line. So we're thinking back to, what do we do that in chapter 12? Writing the parametric equation of a line. Does anybody remember the expression for parametric equations of a line? X. So that's a symmetric equations. So the parametric equation x equals x1 plus at, y equals y1 plus bt, and z equals z1 plus ct, where a, b, and c are the components of the vector in the direction of the line. So this is nice because our x1, y1, z1 can be 0. And what are going to be our direction numbers here, a, b, and c? 5, 3, 2. So our vector is just the vector 5, 3, 2. So we can write our parametric equations of our line as 5ti plus 3tj plus 2tk. So that's a parametric equation of that's our parameterization of our path. So now we can say r prime is just, this one's nice, 5i plus 3j plus 2k. And we can take the dot product of f with r prime. So f dot r prime for our integrand is going to be 30t squared and remember, I'm expressing my force in terms of my parameter also. So y is going to be 3t, z is going to be 2t. So f dot r prime is 30t squared plus we end up with 30t squared plus 30t squared. So we get 90t squared. And the work is going to be the integral from, and here t is going to vary from 0 to what? To go from 0, 0, 0 to 5, 3, 2? With this as our 1. Work time goes from 0 to 1 of 90t squared dt. And we can evaluate that easily, and we get 30. So our work would be 30 units. 30 foot-pounds, 30 Newton meters, some unit of work, depending on what the units of our force and our distances were. All right, questions on line integrals on vector fields? Okay. Pretty straightforward, right.
Heard you say that yesterday in the lab. It was great.
All right, there you go.